Swayam Prabha. Digital India. Educated India.
So in thinking about what I should talk to you about in these lectures, there are many topics presented themselves as very suitable, but then I decided on one which is used in all subjects, no matter what you're going to do. That has to do with elementary notions of what probability theory. The other advantage it has is that probability is one of the most misunderstood subjects of all. And this, of course, is immediately apparent in our daily discourse. We find that the people misuse the concept of probability. They make arguments which are fallacious or wrong arguments based on probability and so on. So I'd like to talk to you about probability to start with, and then we go on to a little bit of statistics and probability distributions and so on. The applications are plentiful, so I won't name any specific applications except a few cases, but then they're plentiful all around you. The mathematics needed for it is at the same time very simple and very sophisticated, depending on the level at which you want to approach it. Probability theory itself was put on a firm mathematical foundation, a rigorous mathematical foundation in the last century, around the middle of the last century, the earlier part of the last century, by people like Kolmogorov and Smoluchowski and so on. We're not going to go into the history of it, but I'm going to give you a large number of examples which we can work out. So we will essentially work out a few problems in probability theory and see how it's applied. And you will find it appearing in surprisingly large number of places. Okay. Here is an argument. Let me start with an argument which is fallacious, which is wrong. It is so often used in daily life that we don't even realize that this argument is being used. Take a lawn where blades of grass are growing. There are millions of blades of grass growing on this lawn, assume. And I take a cricket ball and throw it up, and it lands somewhere on this lawn. It hits a blade on which there is an ant, and it crushes the ant. It injures the ant. And the ant thinks to itself, this has got to be by design. It's purposeful. It's not accidental. And the reason the ant says it's purposeful is because it says of the millions of blades of grass on which the cricket ball could have landed, it landed on my blade of grass and injured me. Therefore, it should have been done with great premeditation and by design. And it's not random at all. Would you agree with this argument?
No, sir.
What's wrong with it?
It's just that the probability is
Let's suppose there are a million blades of grass and the probability that it lands on any one is 1 in a million. But it happened. 1 in a million is a small number, 10 to the minus 6. But it happened. So the ant says that's got to be by design. The probability is too small that it would have hit me, but it hit me, therefore it's got to be by design. Would you agree with that? No. Why not?
we might say that we place an ant on every blade of grass.
Yeah.
And then every ant would say it's
Yeah, exactly. There's an ant on every blade of grass, let's assume. And one of the ants has got to be hit, so this ant got hit. And it says it was deliberate by design. But we see this argument being given all the time in daily life, that this has got to be by design, because it's too intricate and too complex and a smaller probability for it to happen randomly, therefore it's happened to me, therefore it's by design. Completely wrong argument, because now you're talking about after the event, after the ball has landed on some blade of grass, the probability that it would hit that blade of grass is 1, because it hit that blade of grass. That's the end of it. So you can't now say the probability was 10 to the minus 6, it landed on me, and therefore it's got to be by design. Now a lot of things in daily life, like astrology and so on, are based on arguments like this. They're based on purely anecdotal evidence to start with, but they're based on specious arguments of this kind which are wrong. So we'll try to straighten out some of these things and give a proper definition of probability, etc. And I'll start with the simplest machine of all for probability, tossing a fair coin. I toss a coin and it's got two possible outcomes, a head and a tail. And let's use symbols for it. So I will denote the head by H and tail by T. These are the two possibilities and no other possibilities. We are ignoring the possibility that it lands on its edge and remains balanced, etc. We take it to a 0 and the probability of only H and T. If the coin is fair and you make a coin toss, the probability that you get either H or T, the word or is very important, is exactly 1/2. Why do I say that? Why do I say the probability is 50-50 that I'm going to get heads or tails before I make the toss? So what? Uh-huh. We'll do that experiment. We can do it on a computer right away. Those of you who can program a machine, do that right away. Toss a fair coin 100 times and find out if you're going to get exactly 50-50.
On average, you will get 50%.
Now, what's meant by this average?
Both the events are equally.
So, I want to define the statement. What is meant by the saying that the probability of a head is 1/2? I want to define this probability properly and then show that it's 1/2. That's a separate problem, but I want to first define the probability. There are many ways of doing this, but we want an operational definition which you can actually check out. The number of? He says the number of ways in which a desirable event. What's a desirable event here? Okay, so you want the outcome to be what you want, namely the head. Let's take head. H is the head, and I want heads. So what should I do with this coin?
One way in which you can get head, and there are total ways, 2 ways in which you can get out.
Now you're saying that if I toss the coin twice, I'm going to head once and tail once. You didn't say that. So what exactly is, how do you define this probability? When you say I have a 50-50 chance of getting head or tail, how do I define this?
You say that it's very unlikely that you will get something that's far away from you. Like 99
We'll come to that. We'll quantify it. Eventually, we are going to quantify what's the probability that you get 90 heads and 10 tails and so on. We'll do that. But I want to first, even before that, begin by defining probability. How do I define probability at all?
So if you take one coin and you flip it like multiple times, how many ever times you want.
Right?
So then
I conduct the same experiment under identical conditions repeatedly, and then what?
And then you count the number of times you get a head, and you count the total number of tosses which you get. So and then you, for the different experiments in the same ideal conditions, you calculate how many heads out of the total you got and find that ratio. So that ratio.
Okay, he's on the right track. So we do the following. We keep tossing this coin, identical coin, over and over again. Keep track of the number of heads. The rest have to be tails because there are only 2 outcomes, right? And then you calculate the following. You calculate number of heads divided by total number of tosses. You divide one by the other, and then what? I conduct this experiment 1,000,000 times, so the denominator is 1,000,000, and the number of heads, say, was 722,462. So I take that ratio, and then what happens?
So this is like one sample, and then you do the same thing again, and then you get different values of number of heads by total number of tosses, and those.
But that will depend on the total number of heads tosses, right? I get different numbers, but why don't I just do it in one big experiment?
So the ratio. So you do multiple tests.
So as you increase the total number of tosses,
Yes.
the number of heads will approach a specific value.
Right. Approach a limit. You're
It's
guaranteed that it will approach a limit. In other words, if n is the total number of tosses, then this ratio is h over n, where capital H is the total number of heads. Number of times I get little h as the outcome, right? And then you're guaranteed that limit n tends to infinity h over n equal to a finite number which is less than 1, and that's the a priori probability that you get a head. That's the probability before you do the experiment, that you take a coin and look at it and say, what's the probability that if I toss it, I'm going to get a head. Okay? This is called the law of large numbers. There's no reason why this limit should exist. But there are deep mathematical reasons as to why it actually does exist. But this is a good operational definition for our purposes of probability. Because after all, if there is a limit, it means that this number of heads is oscillating about it and then actually tends to it as n tends to infinity. There's no reason why a sequence like this should converge at all. It could just be up and down, flipping back and forth. But you're guaranteed by what's called the law of large numbers that a limit exists and is the a priori probability. A priori means before the fact probability of getting ahead. Right? Now you can easily generalize this to the situation where the coin is a biased coin. Suppose the coin is heavier on one side or on the other and it lands on heads more often than it does on tails. Then there is a probability P which I'll denote by little p. There's an a priori probability P which is a number between 0 and 1 that you get a head on a single given toss, any given toss. If you have only two outcomes in the experiment, P and heads and tails, then the probability of getting a tail must be 1 minus the probability of a head. Because the total probability of some outcome is 1. Some outcome and the other is always 1. So we will say P is the probability a priori of H and Q equal to 1 minus P equal to of T. If P is equal to Q is equal to half, what do you call the coin? It's a fair coin. Otherwise, a biased coin. Okay. Now, a process of this kind, where you have only two possible outcomes, and half the probabilities of the two is equal to 1, is called Bernoulli process. So, if I want tossing this coin, what I am doing is to give a demonstration of a Bernoulli process. And now I am going to do the experiment. Take a coin, and we could as well take a biased coin to start with, because we can solve a more general problem. A fair coin, that's gone. I've got a little p as the probability of a head. Yeah.
So P here is 1 and N here
P is not 1.
P is equal to.
P is a number between 0 and 1. That's the a priori probability that I get a head in a toss. Okay. Why do I say the probability for a fair coin? Let's look at the fair coin first. Why do I say the probability of 4 heads in a row is 1 over 16? No, all outcomes. Yeah, every one of these 16 is equally likely. I understand.
So if you take the probability of each outcome as P,
Yeah.
then all of them are equally likely, so all of them are P. But then the probability of something happening is 1. So 16P is
For 4 heads in a row, what do I need? The first coin turned out to be head. What do I need next for 4 heads?
another head.
It should and. So the first coin should be head, the second coin should be head, and the third coin should be head, and the fourth coin should be head. And the 4 tosses are independent of each other. If they affected each other, that would be different. So the coins are independent of each other. When probabilities of different events are independent, the probability of having both events, this and that, multiplies. So the multiplication symbol is shorthand for the word and in daily language. Think about it. Whenever you say and, what you mean is multiplying probabilities. You want this and that. You want the probabilities of the two to be multiplied, provided they are independent events. If you arrange it magically such that with some magnetic coin or something, that if it's head once, it will be head the next time also, then it's no longer true. This is no longer true. But if they're independent events, you want both events to occur or multiple events to occur one after the other, the probabilities multiply. Okay. What is the probability that you get head, head, head and tail? So let's write down these probabilities for a fair coin to start with. Probability equal to 1 over 16. What's the probability of this?
Should they be in the same order or any order?
I specify the order. I've written the word for you.
Let us
Once I've written the word for you, the matter is over, right?
1 by 6.
Is also 1 over 16. Every one of them is 1 over 16. Now I ask, what is the probability of 4 heads equal to 1 by 16? What's the probability of 2 heads, 2 tails? Now I'm being. Huh? Why do you say 1 over 4? Let's do an even simpler one. Let's always take the simplest example. Just 2 coins. What are the possible outcomes? Head, tail, head, and so on. So now, in the case of 2 coins, what's the probability that both are heads?
1 by 4.
Because it's a product of half times half. And what's the probability of a head and a tail? Why do I say that?
Because there's a HT and a T edge.
Because while each event has got probability 1/4, to get a head and a tail, I don't tell you which one comes first. So you got 1 head and 1 tail, and you can either realize it by HT or TH. So either this or that, and that tells you then you must add the probabilities. So the word and implies multiply probabilities for independent events. Yeah, for 2H and 2T, you have to choose 2 heads out of 4 coins. The number of ways of choosing 2 objects out of 4 is 4C2. And once you've chosen the heads, the rest are tails. So we will write down the explicit probabilities in a minute, in the more general case.
Can you also say that there are 4 factorial by 2 factorial ways where 2H and 2T?
Absolutely.
There will be 6 way total ways.
Absolutely. Exactly. We're going to generalize that statement in a minute. Okay? Yeah, that's 4C2. It's exactly the same as the binomial coefficient. So we're going to write down the general formula, which you can guess immediately. Now I go back and ask a general question. So is this completely clear? When you have independent events and you want 2 events to happen, this or that, then the probability is add. But you want this and that, then the probability is multiply. And at all times the total probability is 1. It's normalized to unity. If there is no total probability conservation, some event happens which has not been included here, then the total probability can be less than 1. Suppose I give you a fair coin and I ask, what's the probability of a head or a tail? And there is a probability 1/8 that the coin falls into a ditch and disappears. Then what's the probability of getting a head?
Probably getting a hit.
7 by 8, 7 by 16.
7 over 16, because there's only 7/8 probability that the coin survives, and then you have half probability that it. Okay, so that's just common sense. Now I'm going to ask, in n tosses, the probability in n tosses of H equal to. First of all, in n tosses, what is the sample space of H? H is the total number of tails in n tosses. Now we're going to do an unfair coin with probabilities P and Q of heads and tails. We're going to toss it n times. We're going to record the results, and I ask, what is the probability of getting a capital H as the total number of heads? What is the sample space of H? What can H range over? First, whenever you talk about the probability of a random variable, you have to specify the sample space. What are the possible sets of values? What's the possible set of values of this number? It could be 0.
0 to 4.
It could be 1. It could be 2. It could be all n. N plus 1 possibilities. What's Pn of H equal to? First of all, you're supposed to get capital H heads. the remaining must be tails, right? So what does this imply? The total number of heads plus the total number of tails must be equal to n, which is a given number, the total number of coins at your disposal. So it's sufficient to work with capital H as the variable, because for a given capital N, t is just n minus h.